look, it's in 3D. All right, sorry. We're gonna do a Bernoulli equation problem. They build up a plaque on the walls of an artery, decrease the diameter from 1.1 centimeters to 0.75 centimeters. If the speed was 15 centimeters per second before the plaque region, find the pressure drop in the plaque region, and then density of blood is 1060 kilograms per meters cubed, which makes sense because blood is primarily water with a little bit of stuff in it, so it's going to be a little bit more dense than water. All right, so you should pause this video and try the video on your own, or try the problem on your own and see if you can do it. All right, pause it. Okay, I assume you pause it. So then we're going to work through it together. All right, so how do I do this? Well, I draw a picture first because, hello, we're doing physics. We always draw a picture first. So here is my artery. At the start, my artery has a diameter of this. The fluid is moving 15 centimeters per second. And then over here, it's gonna find a region. Sorry, I don't know if you can hear, my stomach is really grumbling. You know, I don't know if you can hear that, but yeah. There's the plaque, and then it is going to be separated. Oh, look, see, my stomach's just stopped. Oh, wait, no, there it is again. This separation is going to be 0.75 centimeters. All right, so then we have to identify our important points. So what are our important points? This is going to be one important point, and then in between is our other important point, okay? Then we're going to write out the Bernoulli equation. I'm going to encourage you, write out the Bernoulli equation, the whole thing, every single time, okay? So if I do that, I have rho g y at 1 plus 1/2 rho v1 squared plus pressure at 1 equals rho g y at 2 plus 1/2 rho v2 squared plus pressure at 2. Okay. Remember the way that I think about this? Potential, kinetic, work. I realize it's not actually potential kinetic work, but that's where it came from. And then you think, all right, here's my picture. Is there anything that's going to be the same? Darn right there is. The height's the same, so that's going to cross out. And then it's just a matter of, all right, I got to plug in my stuff. And you can be like, well, I know rho and I know my speed, but shoot, I don't know my speed over here. But you can find your speed over there using the equation of continuity. So, hey, whatever volume, the volume flow rate here has to be the same as the volume flow rate here. So that means V1 over T has to equal V2 over T, which means area 1 times V1 equals area 2 times V2. And if I plug my stuff in, I can then solve. So pi times 0.055 squared times 0.15 meters per second, because I just changed that to meters per second. Isn't that crazy? I can do that in my head. Equals pi times this one I'm going to use my calculator for. I know it's weak. Sorry. 0.75 divided by 100 divided by 2 is going to be 0.00375 squared times V2, and then I can solve for V2. Pi's go away, and then if you do the math, so I get that squared 0.055 squared times 0.15 divided by my previous answer. What? I get 1. Wow, that's amazing. All right, I get 1. So then if I was to plug this in, I'm going to plug that into my equation. 1/2 1060 times 0.15 squared plus P1 equals 1/2 1060 times 1 squared plus P2. So if we're trying to find the pressure drop, that would be P1 minus P2. That's going to be how much it drops. So if I do that, P1 minus P2 equals, and then if I plug my stuff in, I'm going to take this minus this. So 1060 divided by 2 minus 0.5 times 1060 times 0.15 squared equals, the pressure difference would be that many pascals. Okay, that's how you do it. Not too bad. Plug your stuff in. Sorry about the glare. Bye, kids.